From the very beginning we had been talking about light. The whole discussion of relativity revolves around light, speed of light in vacuum, independent of frame of reference, Maxwell's equations giving electromagnetic wave having that particular speed and all those things. Now, this light itself has an extremely interesting history of wave particle dilemma and then finally wave particle duality. In many cases, as Maxwell did, light is treated as electromagnetic waves going with a particular speed in vacuum, which is around 3 into 10 power 8 meter per second and all that. But there are instances where this light has to be taken as a stream of particles, countable separate energy packets. You know the Bohr's Niels Bohr's model. So, when hydrogen atom is in an excited state and one atom, when it de-excites from this excited state to ground state or to a lower excited state, then the difference of energy is that comes out as one packet, which we call photon. So, you can count how many electron transitions are there, those many packets of light have been emitted. So, in that sense you can count that one packet, another packet, another packet. So, it is like stream of particles coming one after the other. Photoelectric effect, you know, is another. Einstein got Nobel Prize for explaining that photoelectric effect in terms of wave particle duality. So, when light is treated as a photon or a particle, it has energy, it has momentum. From Bohr's theory etc., you very well know that the energy of the photon is related to the wavelength as E equal to h times c by lambda. H is Planck's constant, another universal constant, Max Planck, genius who did thermodynamics of radiation, black body radiation. We will talk about this in some other course. And then C is anyway is very well familiar to all of us, speed of light in vacuum. And lambda is the wavelength. It is very interesting that we are talking of a particle. We are treating light as a stream of separate photons. Each photon has its own individual existence, and then we are also talking of the wavelength. So, that there comes this concept of dual nature of light. This same light can be treated as a photon when you talk of energy of an individual photon, and that same light can also be treated as a wave, that time you talk of wavelength. So, it is this, and in your Bohr's theory you have excited state and lower excited state, then this energy comes out and then the light is emitted or radiation is emitted, and the wavelength of that radiation is given by this equation. And not only energy, this photon also has momentum, and that comes out very nicely in what we call Compton effect. American scientist got Nobel Prize for what I am going to describe, Compton effect. If you have X-rays, or in this particular experiment they used X-rays, and those X-rays falling on some material, and then they are getting scattered from here in some direction, making an angle theta. This is that X-ray. So you have an X-ray coming in, then this X-ray falls on a material kept somewhere, and then it scatters, and then at angle theta, if they measure wavelength, this wavelength is more than the wavelength here. So if this X-rays has a wavelength lambda, and at this angle theta they find that this wavelength is different, and this lambda prime, the value of lambda prime depends on this angle theta. So that is known as Compton effect, and experimentally you put your detector here, measure lambda prime, put your detector here, measure lambda time, put your detector here, measure lambda prime, and this way lambda prime as a function of theta can be measured, and that measurement, those values, that pattern is adequately described only if you consider this photon to have a momentum and energy and treat it as one particle. Although we are talking of wavelength because we can measure the wavelength of X-rays, but then when it behaves like a particle, behaves like a photon, that time you talk of energy and momentum, and energy relation is here, and the momentum relation is P is equal to E by C or H by lambda. So if you treat this as a particle, this X-ray as a particle, stream of particle one by one, you have here you have energy of this photon, E is equal to Hc by lambda. Then you have energy of electron. This is scattering, it is supposed to be from electron, and the electron is bound to atoms or molecules, but that binding is very weak as compared to the energy of this photon. This will be in kilo electron volts, and the binding energy will be few electron volts. So you can treat this as if there is a free particle, free electrons. Then energy of the electron you can write as m naught c square. And then you have momentum. Momentum of the photon, which is h by lambda, and momentum of electron is 0. So you take that atom as a scatterer, and then in that atom the actual interaction is with an electron, and that electron can be taken as just a free electron staying at rest, and then you do the dynamics. Here when X-ray photon is scattered in this direction, this electron will go in some other direction, making an angle phi. So before the interaction you have an electron and a photon. After the electron, the photon has changed its direction, and the electron is also, it recoils in some other direction. So after this event, if you write energy, now this energy is Hc by of photon. This is Hc by lambda prime, and then energy of electron is something else. It was m naught c square in the beginning, but now it has something else, can call it some E, and that E will be given by square root of P square C square plus m naught square C4. So this electron now has a momentum P, can call it PE, okay, and you can call this as EE, electron energy and electron momentum. So, the total energy will be this plus this. Then momentum of the photon is h by lambda prime, and that of electron will be this Pe. And now you can write conservation equations, just like particle-particle collision. You have initial total energy, you have final total energy, and total energy should be constant, conservation of energy. So, you have Hc by lambda and plus m naught c square. This is the initial energy before the interaction, and then after the interaction it is Hc over lambda prime and plus E. Then linear momentum. The initial linear momentum is in x direction and is h by lambda, So, in x direction it is h by lambda, y direction 0. After this interaction in x direction, the linear momentum is h by lambda prime times cos theta and plus Pe times cos phi. This Pe times cos phi, this is the component of total linear momentum in x direction, and in y direction originally it was 0. So, after the interaction it should again be 0. So, 0 should be equal to h by lambda prime sin theta and minus this Pe sin phi here, and this was theta, and this sin phi here. Okay. So, in x direction you have h by lambda prime cos theta, in y direction you have h by lambda prime sin theta. Similarly, for this, in x direction Pe cos phi and in y direction Pe sin phi, and this Ee and this Pe are related as Ee is equal to square root Pe square c square and plus m naught square C4. So, you can eliminate from these 4 equations, eliminate phi, eliminate Pe, eliminate Ee. So, from 4 equations you can eliminate 3 quantities, and then you get relation between lambda, lambda prime and theta, and that relation now algebra, only algebra is left. So, you have 4 algebraic equations, and from this you eliminate Pe, you eliminate phi, and you eliminate Ee, and you get finally lambda prime minus lambda, that is the shift, that is the change in wavelength, and that is equal to h over m naught c, Planck's constant, mass of electron and speed of light, and 1 minus cos theta. And this is yes, this is the experimental result also. Experiments also give results which are consistent with this, and which very well shows that light, when it acts as a photon, when it presents itself as photons, it has energy hc by lambda and momentum h by lambda. So, you can do all kinds of dynamics problems where photons are involved. Now, photon by definition is representing light, and light travels at a speed c in all inertial frames, and therefore, photon also travels with speed c in all inertial frames. The speed of photon is that c in all inertial frames, therefore, in no frame it can be brought to rest. and therefore there is no concept of rest mass relevant or applicable to photons. But if I do some mathematics and try to see that if I use that particle relation for photons, energy, momentum and rest mass, what happens? So, for a particle, material particle, we have E square is equal to P square C square plus m naught square C4. For photons, we have E equal to hc by lambda and P equal to h by lambda, and therefore E square is equal to P square C square. E square is equal to P square C square. This is P square and then C square, and here E square, they are equal, and hence if I put in this equation, m naught square C4 is 0 or m naught is 0. So, though it is not necessary, it is not useful, it is not very practical, but still people call this m naught as rest mass energy of the photon, rest mass of the photon, and say that photon has 0 rest mass. So that this formula can be uniformly applied irrespective of whether you have photon or you have material particle. And therefore, photon is said to have 0 rest mass. And conversely also, if a particle has 0 rest mass, what will happen? If a particle has 0 rest mass, then you will have these relations, E is equal to Pc, and E is equal to Pc. If you work out what is the velocity needed, that velocity needed will be c, because if you want to have energy E, which is m naught c square over square root of 1 minus v square by c square, and if m naught is 0, and you have this energy as non-zero quantity, the only way possible is V equal to C. Then perhaps it is 0 by 0, which is indeterminate, and therefore it can have any value, and therefore it can have this particular value also. So, if m naught is 0, then for a finite energy, this V must be equal to C. And similarly, momentum P m naught V over square root 1 minus V square by C square, same story. If m naught is 0 and this P is not 0, the only way it is possible that this quantity is 0. This is not 0, this is 0, then this multiplied by this becomes 0, and therefore this is 0. So, if a particle has 0 rest mass, it must move with velocity c, any particle. In past, people thought that neutrino is such a particle. Neutrino is such a particle which has 0 rest mass, which moves with velocity c, which is not a part of electromagnetic radiation. It is not a combination of electric field, magnetic field. It is not given by Maxwell's equation. So, we have a different kind of entity which moves with velocity c and follows all our relativistic equations. But in this century, beginning of this century, there were very interesting, very meticulous experiments which established that no, neutrino does have small rest mass. How small? People are working on that, but guess is that could be around rest mass energy 10 electron volts. Remember, electron rest mass energy is 511 kilo electron volts. So, that is the kind of thing which is there with photons. We say that its rest mass is 0, although that physically rest mass does not mean much for a photon, because never at rest in any frame, and therefore, no meaning of rest mass as such. Now, let me do a problem with involving this photon before I close, and the problem is on pi meson. There are particles called pions or pi mesons, 3 kinds. One is neutral, and one has positive charge, and one has negative charge, and my problem is with this neutral pion. Now, this particle, this neutral pion, is a very unstable particle. If you produce it in some collision or something, then its lifetime is something like 10 power minus 7 of that order, 10 power minus 17 seconds. In that 10 power minus 17 seconds, it decays, and decays to what? Decays to 2 photons, decays to 2 gamma photons, gamma plus gamma. So, again mass energy conversion. You have a mass, its rest mass, okay, its rest mass is a material particle. Its rest mass is some 135 MeV by c square. So, it is a little more than 200 times electron mass. So, that is its rest mass, and this rest mass is converted into energy, and 2 photons come out, one is gamma, another is also gamma. Now, our question is that we have a pi meson of energy, of kinetic energy 200 MeV. Pi 0 particle moving with kinetic energy 200 MeV decays in 2 gamma photons. One of the photons move along the original direction of pi naught particle, and the other opposite to it. Find the energies of the photons. Okay, a pi naught particle moving with kinetic energy 200 MeV decays in 2 gamma photons. One of the photons move along the original direction of pi naught particle, and the other opposite to it. Find the energies of the photons. So, you have this particle, and this particle moves in some direction. The kinetic energy is given 200 MeV, and this particle is pi naught, and therefore, we know that the rest mass energy is is 135 MeV, and then it decays into 2 photons, and one photon moves in the original direction, and the other photon moves in the opposite direction. So that is how two gamma photons are generated and they move. Both of them move with the same speed c, because photons always move with speed c. Okay, so we have to find the energy. So let us say this energy is E1 and this energy is E2. So total energy conservation, conservation of total energy. So this total energy here is total energy. Here is 200 MeV plus 135, that is 335 MeV. That is how we define our kinetic energy. Total energy minus rest mass energy is kinetic energy. So this is total energy, and here the total energy is E1 plus E2. And so we will have our equation as E1 plus E2 equal to 335 MeV. We need E1 and E2 separately. So the other quantity we have with us is linear momentum, and you can write the linear momentum of this particle before the decay. So if I put this equation number 1 and then work on the linear momentum of this, the linear momentum of this particle, one can find p square c square is equal to E square minus m naught square c4, and this is 335 MeV square and then minus 135 MeV square, and this you can work out. This is 200 multiplied by 470 MeV square. I am using that a square minus b square equation. A minus b is 200 and a plus b is 470. So it is this much, and this will be 3 times zeros and then 4 here and 9 here, this MeV square. And from this side, if I write the linear momentum will be, the total linear momentum will be E1 by c and minus E2 by c. That is the total momentum, and therefore E1 minus E2 is equal to P into C. E1 minus E2 is equal to square root of this. E1 minus E2 is equal to square root of this, that is 9, 4, 000 and then MeV, and that is 306.6 MeV. And E1 plus E2, you know what is E1 plus E2, it was 335 MeV. So you add them, you get E1 to E1 is equal to 1 here, 4 here, 6 here, that gives me MeV, and that gives me E1. E1 is 320.8 MeV. And then E2 you can get, subtract this from this. E1 plus E2 is 335 and E1 is this, so it is just 14.2 MeV. E2 is 14.2 MeV. So these will be the energies of the two photons which are coming in opposite directions. Of course, in our frame in which this kinetic energy is given, these are the results. If you see from some different frame, same pi naught meson pion, and that will have different kinetic energies, and these energies will be different. So the two photons are coming, view from any frame, they will have the same speed c, but the energies will be different, and therefore the correspondingly wavelengths will be different.